We can now put that into a formula, and we get that the price, remember this was the formula for the price of the option, is this expression. So where does this expression 10.3 come from? Let's do the algebra. We have that delta S plus B, by the formulas we just saw, are the dividend present value of the difference in exercise values times S. And then we have the present value, B, is the present value of U, CD minus DCU over U minus D. So that's what we start with. Notice the S's cancel out, and we can write this expression. We'll factor out a present value term, and we get e to the R minus delta H CU minus CD over U minus D. And then we have the other term is UCD minus DCU. So now all we have to do is collect terms. We're going to have a coefficient of CU and a coefficient of CD. And when you just simply collect the terms, they're both going to be over U minus D. That's the common denominator in all my expressions. And you can see that the coefficient of CU is e to the R minus delta H. And then I pick up a minus D from the second term. And the coefficient of CD is a U minus this exponential. And that's just what we saw a moment ago. Namely, that we can look at this price as a present value of exercise values of the option, where I have two coefficients, this term and this term. And we're going to investigate these in a minute. Now, it turns out we have a no arbitrage condition, namely that this value, and let's recall what this is. This is the risk-free return on a T-bill minus the dividend rate. Has to be less than U, has to be greater than D. Perhaps if I rewrite this, it'll be more obvious. Another way of saying that is e to the RH has to be bigger than D, e to the delta H, and has to be smaller than U, e to the delta H. Let's look at what this says. This says that the return on a T-bill has to be bigger than the worst. This is the total return on the stock now, right? We have a D is the price effect on S per share, and e to the delta H is the extra shares we get by buying or reinvesting dividends. So this says that the risk-free rate of interest has to exceed the worst return on the stock and can't be better than the best return, total return on the stock. And that makes sense, and that would be enforced by arbitrage. Again, imagine if e to the RH was less than delta. So let's, in fact, investigate that in our next blank slide. Let's just do one of these examples. Imagine that the T-bill, e to the RH, was bigger than the total return on the stock. Either bigger than or equal to. So we're saying that, so I'm now violating that set of inequalities, that the T-bill return is at least as great as the return on the stock. So what I'm going to do is I'm going to arbitrage this by going long T-bill, and I'm going to short one share. I'm going to short a T-bill I'm going to go, so I'm going to short one share, and that's going to give me S0, and then I'm going to go long a T-bill. So what happens at the end of a period? Well, my T-bill, my long position, goes from S to S0 e to the RH. My short position does one of two things. It either becomes S0 U e to the delta H, or it becomes S0D e to the delta H. Now, by assumption, this is bigger than this, and of course that's bigger than that, so I have an arbitrage. It costs me nothing at time 0, and I make a profit if the stock price goes down, and I make a profit or come out even if the stock price goes up. So this arbitrage would enforce that ultimately the inequalities that we saw will prevail. And it would be the same if you do as a exercise if e to the RH was smaller than the down return. It would be exactly the same. In that case, I would go long the stock and I would short the T-bill.